Okay, in the last lecture, we started spectral clustering because it has close connection to a technique in dimensionality reduction. And spectral clustering by itself is a topic of this course because the next half of the course we will talk about clustering techniques. So in spectral clustering, the setting of the problem was that we have n data points. We make we have n data points and we make undirected weighted graph of this n data points. And eventually we discuss cut and the ratio cut, and we realize that it's better if we minimize ratio cut of A and A bar and make the graph to two parts. Then we defined a vector f, which was n-dimensional, and we defined fi to be cardinality of A bar over A square root and negative of cardinality of A over A bar. And this is when xi is in A and if xi is in A bar, a complement. Okay, so that was the definition of f. And we proved that by this setting, by this definition, minimizing ratio cut is equivalent to minimizing this cost function. So we would like to minimize ratio cut, but it's equivalent to minimizing this cost function when wij is weights on edges of this graph, which basically shows the similarity between points, similarity between two nodes I and j. Okay, so we need to minimize this. And W is known, similarity between points. Fi and Fj are unknown. If we find Fi and Fj for each point, I and j, then basically we have the labels of these points. If F turn out to be positive, we assume that it's in class A. And if it's negative, then it's in class A complement. So basically, by computing these labels, we can cut the graph in two parts. Okay, so that's the goal. So we know up to this point. Now I have another claim. So the claim is that this cost function, wij fi minus fj squared, actually one half of this, is equivalent to f transpose, the vector f that we defined here, LF. When L is the Laplacian of graph G. Okay? Okay. what is Laplacian? Laplacian of a graph is d minus w. When w is n by n weight matrix. So basically W is a matrix that captures the similarity between all points pairwise. So it's n by n. For any two nodes, you put the similarity of that two nodes here. Okay? So that's similarity of 1 and 1. That's similarity of 1 and 2. That's similarity of 1 and n. This is similarity of n and 1. And this is similarity n of n. And D is a diagonal matrix of this form. D1, D2 to Dn. So it is n by n matrix, but it's diagonal. So all of diagonal elements are 0. In diagonal elements, di is basically summation of wij over j. So it means that you add elements of this row of the matrix. This summation would be d1. And you add elements of the second row. This summation would be d2, and so on. So basically, each row of matrix W, you add it up. And the value would be the diagonal value of matrix D. Okay? Is that clear? Okay, now if you compute D minus W, this is Laplacian of the graph. And Laplacian has some properties. But now I have to prove this claim that minimizing or this cost function is equivalent to this cost function. So if you look at this quantity, F transpose LF, it is basically F transpose D minus W F, which is F transpose DF minus F transpose WF. Okay. So what is F transpose DF? D is a diagonal matrix, and you multiply a row vector on the left and a column vector on the right, the same vector. So in terms of summation, I can write it as DI Fi squared over I. You know, because any off-diagonal element would be 0, so only diagonal element will be multiplied by elements of F from left and right. So it's going to be Di Fi squared. One of the F comes from the left, one from the right. Okay, that's what F transpose Df is. So the second term, F transpose Wf, how can I write it down in terms of summation? You know, it's going to be F transpose WF. It's going to be a scalar, right? Because F transpose is 1 by n, then you have n by n, and then you have n by 1. It's in a scalar. So it's summation of some elements. What are those elements? Those elements are basically Wij Fi times Fj over all I and j's. Okay. Okay, now I have this quantity. I'm going to put 1/2 in front of that and multiply each of these terms by 2. Okay, so I have 1/2 I have 2 sigma di fi squared. So I have 2 of them. I will write it as di fi squared plus di fi squared. Do you mind if I change this I to j? This is just an index, right? I goes from 1 to n, j goes from 1 to n. It makes no difference. And I have this term, which is 2 wij fi fj. Okay. So that's 1/2. Remember the definition of di. di is summation of wij over j. Basically, this term, I can write it as summation over I fi squared. And instead of di, I can put summation over j of wij, because that's, by definition, di. And I can do the same thing here. That's going to be summation over j of fj squared. And dj would be summation over I of wij. Yes?
Do we have plus sign? Should be a minus sign. Is it -2 or +2 for wij fi fj?
Yeah, thank you. Yes. And then I have the last term, which is -2 sigma wij fi fj squared. Okay. So this term, actually, I can write it as ij wij fi squared. Right? This fi doesn't have index of this summation. I can take it inside. And this term, the same, would be summation over ij of wij fj squared. And the last term is -2 sigma ij wij fi fj squared. Okay, what this summation is, wij fi squared, fj squared minus 2fi fj. Yes?
Is that where it's supposed to be on the outside of the bracket?
Yes.
No,
Let me see. It doesn't have squared, actually. We just, we don't have any square here. We just expand this, expand it, expand. No. Is that right?
There's a factor to that,
That was the claim. So we want to prove that this is equivalent to this. I started from left-hand side, and I started to expand it. There is no square.
Yeah, so I'm saying that line right there, that's a perfect square.
Which line?
The last one.
No, there's no square here.
The question you asked before. Forget it, never mind.
There's no square here.
Okay.
So fi squared, fj squared minus 2fi fj. What that is? So you meant to answer to this question? Okay, sorry, I thought, because I usually make mistakes when I do math. I thought you're pointing to one of those mistakes. Yes, it is fi minus fj squared, exactly. So it is 1/2 wij Fi minus Fj squared. And that's basically our claim. That 1/2 of this is equivalent to this. So we start from left-hand side and we show that it's equivalent to right-hand side. From right-hand side, we started to show that it's equivalent to left-hand side. Okay? So we wanted to, to minimize the ratio cut, we realized that we can minimize this. And then we realized this is equivalent to F transpose LF. So to minimize ratio cut, I can minimize F transpose LF. Yes?
So just going back to the first minimization of the sum, are we minimizing it over A and A power, which kind of like controls F? Is that the variable we're minimizing with respect to?
Here you are minimizing over F. F is unknown. So I can minimize F transpose LF. L is Laplacian of the graph, which is a known quantity, and F is unknown. I'm minimizing over F. Okay. So I have a much simpler problem now. So if I want to minimize F transpose LF, F is unknown vector and L is a known matrix. What would be the solution? We had this many times by now. Sorry? It would be 0 without constraint. So I need to add a constraint to this problem to make it well defined. So the actual constraint that I have is this constraint. That if I should have this value if I is from A, and this value if I comes from A complement. But I cannot actually solve the problem using this constraint in an efficient way. Okay, so it becomes a pretty hard problem. So I just relax this constraint. I can't satisfy it. I can't relax. I just relax it. I put another constraint. And then I can solve the problem efficiently. Values of F are not going to be equal to these quantities. They have different values. But they're going to be positive and negative. Any positive point, I will assume it comes from A. A negative point, I assume it comes from A complement. Because it's impossible to solve the problem using that constraint in an efficient way. Okay. You have a question?
So are we no longer minimizing ratio cut?
Well, we minimizing an approximation of ratio cut. A relaxed version of ratio cut. So this is a problem pretty similar to the second step of LLE, right? What is the solution for F? In LLE, I had minimized trace of Y, M, Y transpose. And the solution was minimum eigenvector of M. And the first eigenvector was corresponding to 0 eigenvalue, right? So that's exactly the same. The solution to this problem is minimum eigenvector of L. But the first eigenvector has an eigenvalue equal to 0. You have to ignore that one and take the second smallest one. So F will be the second smallest eigenvector of L. The first one has an eigen value equal to 0. Okay. So you compute F, and if F is n-dimensional. For any Fi, if this is positive, this point belongs to cluster A. If it's negative, this point belongs to cluster A complement. Okay? Let me show you some result of a spectral clustering. Okay, suppose that's our data set, and we want to cluster it in two parts. What you see on the left what you see in the left is the result of clustering if you apply k-means clustering, which we haven't learned about yet. Most of the clustering techniques will produce a result like this. And this is the result of a spectral clustering. So as I told you at the beginning, there is no correct and wrong solution here. You can't say that this is a wrong solution, that's a correct solution. The only thing that I can claim is that the solution on the left is closer to our perception. We as human being, if you give me this data and ask me to cluster them, most of the people will choose the one on the right, most likely, because it's just two circles. And this is another example for the paper when it appeared in NIPS in 2001. And the data set is just NIPS 2001, and they tried to cluster it in 8 clusters, and this is the result of k-means again. K-means put 2, 0, and a part of this 0 and a part of 1 in one cluster, and a part of 0 and part of 1 in another cluster. But a spectral clustering take each alphabet or each digit as one cluster. And this is another example. In this data set, we have like 3 clusters, for example, here. And each line is clustered in differently from the other. But if you do k-means, a part of each of this line would be in one cluster. Okay? Any question? So the algorithm that I presented here, the assumption was that we are basically cutting the graph and make it 2 parts, right? But here you have 3 clusters, not 2 clusters. We have 3 clusters. So in fact, a spectral clustering easily can be extended to more than 2 clusters. So this part, this extension, doesn't have a strong theoretical background like what we proved here. It's more heuristic. The way to cluster the data in more than 2 clusters, if you have 2 clusters, you take a vector, the smallest eigenvector, and then you decide based on the sign, negative and positive. But suppose that you want to cluster the data in 3 clusters, for example. In this case, you will take 2 eigenvectors of L, not only 1. If you want to cluster data in k clusters, you take k minus 1 eigenvectors. Okay? So if you would like to cluster the data in k clusters, take the k minus 1 eigenvectors. And then how can I decide? So I have taken, when I had only one vector, based on the sign of element of this vector, I could decide that points are in this cluster or the other. Now I have two vectors, and I have three clusters. How can I decide? So usually we run a clustering algorithm on these two-dimensional vector, like k-means, for example. So you want three clusters. You take two eigenvectors. These two eigenvectors, f, let me show it by capital F, because it's a matrix. It's going to be two-dimensional. It's like n by 2 instead of n by 1. It's n by 2. Now I want to split it in three parts. Usually people run k-means clustering on this with three clusters. And then, so this portion end up in cluster 1. So this basically shows the indices of the point that are in the first cluster, and so on. Okay? So L is Laplacian. And I told you one of the properties of Laplacian is that the number of zero eigenvalues shows the number of components in the graph. So if graph is connected, you have one eigenvalue equal to 0. If it has two parts, it has two eigenvalues equal to 0. So now you can see the reason that in LLE, we discard the first eigenvector, and we said that in LLE, the first eigenvector always corresponds to an eigenvalue equal to 0, because in LLE, the matrix that we decompose is I minus W times I minus W transpose. So look at I minus W. I minus W is Laplacian, right? Because Laplacian was D minus W, and D was a diagonal matrix such that each element of diagonal is summation of a row. So summation of a row on W is 1, because that was one of the constraints in the first step of LLE. Make sure that each point can be reconstructed by a set of weights such that the summation of those weights is equal to 1. So if you sum one row of W, it's always 1. So basically identity matrix is D here. Okay? So I minus W is Laplacian. And what you have here is Laplacian times Laplacian transpose. Basically, it's Laplacian squared of the matrix. Okay? And if Laplacian squared and Laplacian have exactly the same set of eigenvectors. Just eigenvalues will be squared, but it has one eigenvalue equal to 0. When you square it, it's still 0. Okay? Any question? Yes?
Right there it says if you would like to cluster the data into 8 clusters, that's supposed to take the k minus 1 smallest eigenvectors?
Yeah. Yes. After discarding the one which is corresponding to 0. Okay. Any question? Yes?
That relaxation over square the F transpose F being 1, how do we come to that relaxation from that piecewise?
How do
we arrive at that relaxation from the original constraint?
we just got to this point, and we had this proof that sign of the basically elements of F are indicators of clusters, positive and negative. But the constraint is that they have to have certain values, which we can't do it. So that's basically the part that we are relaxing. I cannot maintain this certain value in F, any value, but what I'm going to care about is the sign. Any value with positive, any value with negative. That's basically, it's not a big relaxation. It's a small relaxation that You don't force elements of F to have certain values according to the cardinality of set A and A bar. Because at the end of the day, we wanted to cluster points based on the sign. Still do the same thing. Okay. Okay. Okay, Laplacian, a spectral clustering is closely related to a dimensionality reduction technique. It's called Laplacian Eigenmap. Okay, Laplacian Eigenmap, similar to LLE and isomaps. Laplacian Eigenmap is dimensionality reduction technique which can take care of nonlinearity, similar to LLE and isomap, and has been introduced after those two algorithms. Similar to those, has in the first step construct a graph out of the data. So in the first step of Laplacian Eigenmap, we construct a weighted graph G from n data points. Weights on each edge is similarity between 2 points or connectivity of the points. So define Wij to be 1 if I and j are connected. 0 otherwise. So you have a graph. If 2 points are connected, if there is an edge here, the weight of this edge is 1. If there is no edge, it is 0. So alternatively, this W can capture similarity between points. So basically, this W could be anything. But that's the most common one. So as an alternative, Wij could be a measure of similarity between points. For example, it could be e to the power of xi minus xj squared divided by some gamma, which is a measure of similarity. Yes?
By connected, do you mean there's a path between them? Or
Yeah, there's a path between them. So you make, say, for example, a k-nearest neighbor graph. And if points is one of the k-nearest neighbor, then W is 1. Otherwise, W is 0. Okay? So then Laplacian Eigenmap minimize this cost function. Wij yi minus yj squared. And y is unknown. Or let me put capital Y. So this yi's, the setting is similar to the setting that we had before. X is in Rn, Rd, and y is in Rp. So I'm trying to reduce the dimensionality from d dimension to p dimension. Y is unknown. So Laplacian Eigenmap suggests to make to construct a graph, set weights for that graph, and then minimize this objective function. This objective function, as you can see, is very similar to the objective function, or is identical to the objective function that I had for spectral clustering, right? except that in a spectral clustering I had F here. And this, I have Y here, which is my low dimensional representation. So intuitively, this objective function makes sense for dimensionality reduction, because if 2 points are far apart, suppose that I want to minimize this cost function. If 2 points are far apart, then Wij would be 0. So nothing would happen with any values of Y. So if 2 points are far apart, I don't care about the values of Y. If 2 points are close to each other, then Wij would be a large number. So in one case, it's going to be 1, right, if they're connected. If they are connected, how can I minimize this term if Wij is large? By choosing Yi and Yj to be close. So basically, this objective function tells me if 2 points in high dimensional space are close to each other, they should appear in low dimensional space close to each other. If 2 points are far apart, I don't care. That's exactly what, not exactly, but that's what we wanted to do, when we try to unfold this Swiss roll. We realized that points that are far apart on the manifold, the Euclidean distance is not valid anymore. But in a locality, I can basically model a locality of a point as a linear patch. So similarity in a local area of a point, local domain of a point, is valid. But similarity between points that are far apart is not valid anymore. So this objective function basically preserves the locality for close by point in low dimensional space. Doesn't care about points that are far apart. You may think that it's a disadvantage. This part is a disadvantage of this objective function, because really what you want is that points that are far apart appear far apart in low dimensional space, right? If 2 points are on the manifold are far apart, you want to sort of stretch them because you want to unfold it. But this objective function assumes that it's going to happen. I'm going to care about local points, and when I preserve it, then it will be, those points will appear far apart eventually, which may not be true in some cases. But the only thing that we are preserving is locality. So if I want to minimize this objective function, that will be exactly the same with the same token that we talked about for spectral clustering. I can rewrite this cost function in this form. Except that Y in that case was just a vector. Y here is a matrix. This here actually I have a D by N matrix, and here I have a P by N matrix. So it's a matrix that I need to compute, a P by N matrix. So you can write it down and see that the only difference with the previous cost function is that it's going to be the trace of Y transpose Ly. And it's stuff just Y transpose Ly. And minimizing the trace of Y transpose Ly is similar to minimizing F transpose Ly without constraint. It's ill-defined. It has a trivial solution that you want to avoid. You add a constraint to this problem that Y transpose Y is identity, and the solution would be eigenvectors of L. Any question? You may see intuitively why spectral clustering captures like alphabets separately or captures a circle separately when k-mean cannot do that. K-means clustering is a clustering on the original space here. A spectral clustering is a clustering on this domain, Y. you saw that when we are clustering the data in 3 clusters, we take the first 2 eigenvectors, which is a 2 by n matrix here, and we do k-means on it. So basically, k-means is a clustering on domain X. A spectral clustering is k-means on domain Y. So as if you're doing dimensionality reduction first, you're extracting some feature of the data, and then you're doing clustering in this domain. So you're doing the clustering on the unfolded manifold of the data, okay, instead of on the data originally. And if points like close to each other appear close here, you have a better chance to capture the right cluster. Okay, any question? So we had many different dimensionality reduction algorithms so far. I can show a unified framework now to basically capture all of these algorithms under the same umbrella. You know, we did LLE, and LLE was eigendecomposition of a matrix, and MDS was eigendecomposition of a matrix, kernel-PCA, dual-PCA, LLE, isomap, Laplacian Eigenmap. All of them are eigendecomposition of a matrix. Now, I'm going to claim that all of these algorithms are kernel-PCA, in fact. Okay? Only with different kernels. So remember that in kernel-PCA, we computed K as n by n matrix, which was a measure of similarity between points. And then, in order to map the data in lower dimensional space, do you remember how did we calculated the low dimensional representation of the data in kernel-PCA? Yes.
Sigma V transpose.
Exactly. Sigma V transpose when V was eigenvectors of K and sigma was like diagonal eigenvalues. And what about reconstruction? Can we do reconstruction in kernel-PCA? We can't. We cannot do reconstruction. Can we map out of sample point in kernel-PCA? And what was that? Y for out of sample was I think it was sigma inverse V transpose and a kernel of X and new data point sample point X. And we are not able to do out of sample reconstruction for out of sample. So basically using kernel-PCA, we can map the data in lower dimensional space by decomposing this kernel, and we can do out of sample. Okay. Now let's look at all algorithms that we had so far. So we had PCA, and we realized that PCA is identical to dual PCA. PCA is the composition of XX transpose. Dual PCA is the composition of X transpose X. So in PCA, basically K is simply X transpose X. So PCA is kernel-PCA with a linear kernel, right? Okay. So what about MDS? In MDS, we decomposed K when k was minus 1/2 h d h. And H was centering matrix, a constant matrix. So I can claim that MDS is kernel-PCA, but the kernel has this form. You know, kernel is a measure of similarity. I measure the similarity between points using Euclidean distance, double center Euclidean distance, and construct a kernel out of that. And that's MDS. What about isomap? Isomap is a kernel-PCA when k is minus 1/2 h d h, but this d is geodesic distance. It's not Euclidean distance. So if you measure similarity between points using geodesic distance instead of Euclidean distance, it leads, kernel-PCA leads to isomap. In LLE, so, in kernel-PCA, it always goes for the large eigenvalues, right? In LLE, we computed the smallest eigenvalue of I minus W times I minus W transpose instead of large eigenvalue. So can you show me a matrix such that its largest eigenvalue is equal to the smallest eigenvalue of M? Basically, I'm looking for a matrix that has the same set of eigenvectors as M, but the order of eigenvectors are reversed. Yes? No. Yes?
M inverse?
M inverse. Or M pseudo-inverse. M pseudo-inverse has exactly the same set of eigenvectors of M, but the order of eigenvectors are reversed. And you can see that, M is symmetric matrix. If you do eigen decomposition on M, it's U sigma U transpose. If I compute pseudo-inverse of M, that's going to be inverse of U transpose, which is U, inverse of sigma, and inverse of U, which is U transpose. But inverse of sigma, all elements of sigma are positive, right? Sigma is like sigma 1, sigma 2, all positive numbers to sigma whatever, d. So sigma inverse basically would be 1 over sigma 1, 1 over sigma 2, 1 over sigma d. So if sigma 1 is the largest eigenvalue, then 1 over sigma 1 would be the smallest one. If this is the smallest one, it's going to be the largest one, right? So basically, set of eigenvectors is the same in M and M pseudo-inverse, but the order will be flipped because of the sigma inverse. So I can think of this M inverse or M pseudo-inverse as a kernel. It's a positive semidefinite matrix. I can think of this as a kernel. As an alternative, if lambda max, or if sigma max is the maximum eigenvalue of M, then sigma max times identity minus M has the same set of eigenvectors, but the orders are flipped, basically, you know. I just subtract the maximum one from all of them. Yes?
In the pseudo inverse of M, what happens to the eigenvalues that are 0?
So you already ignored those, you know. You always can make a sigma which has no zero eigenvalues, because those zero eigenvalues will knock down this. I mean, those eigenvectors corresponding to zero eigenvalue, they are not in the space, on the space of M. They are on the null space. We're decomposing the space, not null space, right? You can basically ignore those. So in LLE, let me write it here. In LLE, define K to be M pseudo-inverse or sigma max I minus M. Then it's kernel-PCA again. But not exactly kernel-PCA. Because solution of kernel-PCA is sigma V transpose. Solution of LLE is just eigenvectors of M. So I don't multiply this by sigma. Sigma is set of eigenvalues. When I multiply V by sigma, means that I rescale each direction of V according to corresponding eigenvalue. So each eigenvalue shows the variance in that direction. I rescale each of these directions according to its variance. That's not happening here in LLE. So we do just eigen decomposition of M, but we don't multiply this by any eigenvalue. And that's the reason that solution of LLE is always sort of spherical. You know, if you have a rectangle in high dimensional space, it becomes square in low dimensional space. It doesn't capture the variance of each direction. All directions have almost the same variance. Okay, and that's due to the constraint that it has. So LLE is kernel-PCA. Up to scale. So the solution is kernel-PCA, but the scale of each direction is different. And same for Laplacian Eigenmap. In Laplacian Eigenmap, we are doing eigendecomposition of L. We are taking smallest eigenvectors. Just define K to be pseudo-inverse of L, or define K to be maximum eigenvalue times I minus L. In kernel-PCA, we are able to map out of sample point. And to do out of sample point, we need eigendecomposition of the kernel, sigma and V transpose. We also need the value of the kernel, x and x bar. Out of sample x. This is like a vector, right? One of the rows or one of the columns of this kernel. So can we do out of sample in isomap? Or in LLE or in Laplacian Eigenmap? We can't, because here actually in kernel-PCA I use a closed form kernel. You know, my kernel is RBF. You give me a new point, I put the value of this new point in the formula of the kernel and I compute this value. In LLE, in isomap, in Laplacian Eigenmap, the kernel doesn't have a closed form. There's a piece of code which computes this kernel. I have to find the k-nearest neighbor, I have to find the shortest path, and so on. If you give me a new point, I don't know what would be the geodesic distance of this new point to other points. Unless I redo the whole algorithm from the beginning. I add this point to everything and recompute everything from the scratch. Same thing for LLE, same thing for Laplacian Eigenmap. So out of sample can't be done exactly here. But there are approximations for out of sample in all of these algorithms. And kernel actually is supposed to capture the similarity between points. You can assume that isomap captures similarity between points based on their geodesic distance. LLE captures similarity of point based on how a point can be reconstructed by its neighbor. If two points can be reconstructed by the same set of weights, they are similar. Otherwise, they are not similar. Okay. Any question? Yes.
So for the Laplacian Eigenmap, our constraint is y transpose times y is equal to the I, right?
Mm-hmm.
So that basically is saying all the vectors in the p-dimensional space are
orthogonal
to each other.
Mm-hmm.
Is that possible if n is larger than p?
If, sorry?
Is that possible if n is larger than p? So our number of data points is higher than the dimension itself, it's larger than the number of dimensions.
If the number of data points is more than p,
Right, if n is larger than p.
Okay.
So y transpose y is n.
so n is usually larger than p.
Right.
P is smaller
So,
than,
like, so that means the rank of y is smaller than n, right? So y transpose
y transpose y,
would be
the rank would be p.
right.
The rank of the matrix that you are decomposing, L, is n minus 1 because it's Laplacian. Laplacian is always reduced rank because it has one eigenvalue equal to 0. So Laplacian, the rank of Laplacian is n minus 1. The rank of y transpose y is p.
Right.
And p is less than n.
Y is n by n.
Y transpose y is n by n, yes.
Okay.
But it's reduced rank.
Okay, then in that case, that identity matrix is that the whole n by n identity,
Mm-hmm.
but that has a rank n.
Yeah?
But the left-hand side has a rank p.
Y transpose y is n by n, but its rank is p. Doesn't matter. Is there anything wrong with that?
I mean, the constraint says it's equal to the identity matrix, which has full rank, right?
Right. Well, always you're choosing the first p eigenvector of y. Here actually L is not full rank here, is n minus, reduced rank. So you have n eigenvectors. One of them is constant, and there's n minus 1 other eigenvector. So y transpose y would be identity. You have n of these eigenvectors. But when you want to represent it in p dimension, you only select p of them. But you select p of them, right? It doesn't mean that it's full rank anymore. So in terms of notation, this is complete y. This is truncated y, when you choose only the p of columns of y, not all of them. Okay, does it make sense? That's the case everywhere, In PCA, you have D by D matrix, you have D eigenvectors, but you want to go to p dimension, you don't choose all of these p eigenvectors. You choose p of them. Similar in MDS, isomap, LLE, in all of them. You truncate the matrix, you get rid of some of the eigenvectors that are less important. Okay? Any question? Okay, so basically we learned that everything that about dimensionality reduction that we learned in this course from the beginning up to now, in a sense, is kernel-PCA. Kernel-PCA itself is a very useless algorithm in practice. You know, if you want to do dimensionality reduction using polynomial kernel, RBF kernel, usually doesn't help. You know, it leads to a very bad result. But theoretically, it's interesting to know that algorithms that came after that for dimensionality reduction, in a sense, can be interpreted as kernel-PCA. Okay? And these are not things that have been clear right at the beginning. You know, people published IsoMap, LLE, Laplacian Eigenmap, and then someone published a paper said, wait a minute, they're all kernel-PCA. And researchers who did IsoMap or LLE usually don't like this claim to say that your algorithm is this. And no, it's not. Okay, but you can say it this way. Okay, so what we learned of this unified framework, we learned that, okay, everything, I mean, there is a kernel that we can decompose and we can find the low dimensional representation. The difference of these algorithms in difference in kernels. Okay, this understanding of the problem lead to an algorithm which is called maximum variance unfolding, MVU. Okay. Maximum Variance Unfolding, MVU. When they published this paper, the name of this algorithm was Semidefinite embedding. They changed the name afterwards. So first it was SDE, Semidefinite embedding, then they changed the name of the algorithm to Maximum Variance Unfolding. And now it's known by this name, Maximum Variance Unfolding. So what's the idea of maximum variance unfolding? The idea of maximum variance unfolding is that, okay, so in all of these algorithms, you have a kernel that you have to decompose. Let's don't assume any kernel at the beginning. Let's set up an optimization problem and solve for k. What is the optimal k? Try through an optimization process, try to find a k which is best for dimensionality reduction. And then do eigen decomposition on that kernel. Okay? So So basically, the idea, as I said, is to try to find the optimum kernel. And this paper published in 2004. Okay, what is a good kernel? You know, a good kernel, don't forget that kernel is a similarity measure. A good kernel is a kernel which captures similarity in a local patch, you know, at a locality I have to capture the similarity. So if I have a Swiss roll and I want to unfold it at a locality, my graph should have the same geometry. Okay? So basically, if I just look at a local patch, a linear patch, it should look like exactly the same when I unfold it. So these two, up to a rotation and translation, should be the same graph. But that's not true for points that are far apart. Yes?
What do you exactly mean when you say locality? Is it just like a plane that's orthogonal to the...
No, k-nearest neighbor.
Oh, okay, I see.
K-nearest neighbor. So you define the locality yourself. So any point in nearest neighbor of this point, I decide k to be 10 or I decide k to be 100. Or these graphs could be not based on k, based on some epsilon. You know, you can put hypersphere around a point, and any point inside that is in your locality. Okay. So how can I make sure that my kernel preserves the distance, if distance are among the k nearest neighbor is distance of a point in k nearest neighbor. You know, again, you know, that's the general setting that we had. D by n goes to y, which is p by n. So these points, to have n of those, if I look at 2 points, xi and xj, if I look at the distance between these 2 points, if these 2 points are close to each other, I want their distance in feature space of this kernel to be the same. Okay, don't forget that each kernel is basically phi transpose phi. I don't know what the phi's are, but they are. They are equal to some phi, some dot product in the feature space. So my kernel should satisfy this condition. So whatever this phi is, phi xi should be the same distance from phi xj if these 2 points are neighbors. Okay. But we don't know phi. Let me expand this. This is equal to phi xi minus phi xj transpose phi xi minus phi xj. I have a term in the form of phi xi transpose times phi xi. I have a term in the form of phi xj transpose times phi xj. And I have a cross term which is phi xi transpose times phi xj, right? Minus 2 phi xi transpose phi xj. What is phi xi transpose phi xj?
Kernel of xi xi.
It's kernel of xi xi, right? So this is kernel of xi xi. If I have a kernel matrix n by n, kernel of xi xi would be basically kii, the element ii of this matrix. Then I have kernel xj, I have phi xj transpose phi xj, which is kernel xj and xj. And then I have phi xi, phi xj, which is kij. Okay. So I'm looking for a kernel that has this condition for any 2 points that are neighbors. So if xi is neighbor of xj, then xi minus xj squared should be kii plus kjj minus 2kij. That's one condition. What else? Think about other conditions that the K needs to have. Yes?
Symmetry? Kij must be kjn.
It should have symmetry, right? So, like K transpose should be equal to K. K needs to be a kernel. A kernel is what type of matrix? Yes.
Positive semidefinite.
It's positive semidefinite. So K needs to be positive semidefinite. So I can just say that K needs to be a symmetric positive semidefinite matrix. So that's one condition. This is another condition. What else? When we do kernel-PCA, we need to make sure that K is centered. Right? Do you remember centering in KPCA? We assume that phi needs to be centered, and then it leads to some formulation to make sure that K is centered according to centered phi. So K needs to be centered means Kij should be 0 for all I and j. Because I'm doing kernel-PCA. Yes? I can't hear you. Yes. Should be positive semidefinite because it needs to be a kernel. A kernel should be positive semidefinite. Can you think of any other condition? Now I can form an optimization problem, search for a K such that this K is positive semidefinite. Summation of all elements of K is equal to 0 for 2 points that we decide these 2 points are neighbors. Kii plus kjj minus 2kij is equal to some known value because I have xi and xj. I can compute this value on the left, and I can put this constraint on the value of elements of k. Kii plus kjj minus 2kij is equal to this. Do I have a unique solution here, or I have many solutions here? You know, many positive semidefinite matrices, many kernels, could satisfy this condition. You know, we have seen this before. You know, we had kernel for LLE, we had kernel for isomap, we had kernel for Laplacian Eigenmap. All of them capture the locality. So the solution to this is not a unique solution in terms of optimization. It's a feasibility problem, not an optimization problem. So basically by now, I can search for a K which is feasible, means satisfy all of this condition. But can you think of something which really try to find a better K in this search space? That there are many Ks that satisfy these conditions. Can you add an objective function or a constraint to this problem to lead to a unique solution or to a solution which is better among all of those? Yes?
Maximum variance.
You have maximum variance. It's in the name of the algorithm, right? Maximum variance. So how can I make sure that it has maximum variance? Remember in PCA, for example, the variance was summation. The variance of each direction was eigenvalue, and the total variance was summation of all eigenvalues. So the same thing happens here. So if I want the summation, if I want the variance of the whole data, that would be the summation of all of these eigenvalues of K, right? Which is trace of K. So trace of a K is summation of all eigenvalues, is the variance of the data and feature space. So I want to maximize this K. Okay. So basically I can form an optimization problem now, maximize trace of K subject to the constraint that Kii plus Kjj minus 2 Kij for any I and j that are neighbors is equal to a value. K is positive semidefinite, and summation of all Kij's is equal to 0. So we'll discuss this problem in next lecture. This is a convex problem, has a unique solution. Any, yes?
So you just want to maximize the trace of K as well?
We want to that's our objective function, because I want to have maximum variance. Okay.